Alright, so this is the last lesson on just integrals. This is 11.9 improper integrals, and this is the very last skill on Khan Academy. It is skill number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is KAICI number 15. Okay? Improper integrals. And basically it goes like this. Okay? An improper integral is when there is a restriction in the domain that is within the integral, or when that should have said one of the integrals, upper or lower limits, is infinity or infinity. Sorry, I obviously can't type. So what do I mean by that? Well, let's look at these three different situations, see if you can understand. Look at the limits 0 and 1, and look at the function that we're supposed to integrate. Well, does this thing even exist when x is 0? It can't, right? Because x can't equal 0, so 0 is an undesired lower limit. Therefore, it's an improper integral. How about this one? Right away, you should see -1 can't even exist inside here. So it's an undesired lower limit, therefore it's improper. The other situation that we could run into is we can get infinity. See, the upper limit is infinity. Therefore, it's an improper integral, right? That doesn't work. We can't figure out what infinity is. So we have to treat these as a special case. So we can evaluate them by replacing the undesired limit, upper or lower limit, so here was infinity, here was -1, here was 0, with a variable like n, and then we can evaluate the limit of the integral as n approaches the undesired value. I'll explain how to do that in a second. And so we're going to have two situations that happens. It says if the limit of the integral approaches a real number, then it is said to converge to a real number. And if it just approaches infinity or a non-real number, then it is said to diverge. Okay? So just some basic vocabulary there. So I have a couple examples here, and I'm just going to walk you through how we would do these. So remember, I said we can replace the undesired limit with an n. So I can say this is the same thing as 1 to n, but then I have to note that we're going to take the limit as n approaches infinity. Okay, and this is really like saying x to the -2 dx. Now I can evaluate this integral and then evaluate the limit at the end. So let's just kind of work it out. So first off, I'm going to do the antiderivative. Sorry for my weird infinity sign. Well, the antiderivative x to the -2, we add 1 to the exponent, so we get x to the -1, and then divide by the new exponent, which is -1. And we're going to evaluate this thing from 1 to n. Okay, if we clean it up a little bit, this is really saying the limit, as n approaches infinity, of, isn't this really just like -1 over x? It's really all it is. And again, that's from 1 to n. Okay, so one more time, limit as n approaches infinity of, now I can go ahead and plug my upper and lower limits in, and I would call this -1 over n minus -1 over 1. Okay, and now we can see that this is asking for the limit as n approaches infinity once again of -1 over n plus 1. Well, we should recognize that this is one of our special cases. This is the small over big principle, right? So this is relatively small, and infinity is relatively huge. So that means that this equates to 0. So we could say this is the same thing as saying 0 plus 1. And so this answer is 1. So even though it was an improper integral, we were actually still able to find it. The answer is 1, and it converged to 1. If it diverged, there really wouldn't be an answer. Okay, so let's try this next one. What's wrong with this one? Well, if I put a 1 in here, I'd get a 0 in the denominator, so that's no good. So I'm going to write that I really want the limit as n approaches 1 of the integral from 0 to n of, and I'm going to write this a little bit differently. I'm going to write this as 1 minus x to the -1/2 power dx. Okay, Now I can evaluate this. One of the things I'm going to have to do first, though, is I'm going to have to use u substitution. You'll see u equals 1 minus x, therefore du equals negative dx, therefore I can just multiply by negative 1, and dx equals negative du. So let's rewrite this. Again, it's the limit as n approaches 1 of the integral, but now I need new limits because I did use substitution. So if I plugged a 0 in here, 1 minus 0 would just be 1. And 1 minus n would be, well, 1 minus n. And now I'm not evaluating 1 minus x, I'm evaluating u to the negative 1/2. And instead of a dx, I can replace it with a negative du. Well, I'm going to put the du here, put the negative symbol here. This negative symbol, remember, I could just switch these limits and get rid of that negative symbol. And I actually do want to do that because if you think about it, when I go to evaluate a 1 here, 1 minus 1 is 0, so this is actually a little bit lower than this one. So the limit as n approaches 1 of the positive integral now will go from 1 minus n to 1 of u to the negative 1/2 du. Alright, now we're set up, we're ready to actually do this thing. So we add 1 to the power. So don't forget my limit notation. Add 1 to the power of negative 1/2, that brings us to a positive 1/2. Divide by the new power, which is the same thing as multiplying by 2. And then we're going to do that from 1 minus n to 1. Okay. So we can evaluate this a little bit better. This is like saying the limit then approaches 1 of 2 square root 1 minus 2 square root 1 minus n. And now there's no real reason why I can't plug in that limit notation anymore. And so I could say this is really like saying 2, because 2 times square root 1 is just 2, minus 2 times the square root of 1 minus 1. Well, 1 minus 1 is 0. And 2 times 0 is 0, so we really just have 2 minus 0, which is 2. Okay. Pretty fun idea here. I think that it's simple enough, though. I think you guys can do it. I'll see you guys in the next video.